exciting episode. You have me as a substitute introducer because Dr. Shelburne has, I think, a class or lab until 4 o'clock, and he's probably tied up in that. He'll probably come running in about 5 minutes, totally out of breath, and he'll take a seat. But it's my pleasure to introduce a colleague from nearby whom I've known for longer than most of you have been alive. How many of you were born before, let's see, late August 1995? Okay, well, the professors in the back certainly. Okay, so only those few were alive before Dr. Arasu taught here at Wittenberg. He taught here as an adjunct for a couple of years, and we think 95, 96, 97, somewhere around there. And he's back now to give a talk on mathematics. I'm afraid I don't have your talk title memorized because I didn't intend to be the introducer of this speaker.
Don't know what he is.
So without further ado, our colleague from Wright State, Dr. Krishna, oh, excuse me, one more thing. A little memory triggered, I thought, I think I remember his first name is Krishna. So I said, Krishna Athreya, right? No, it's Krishna Arasu. Krishna Athreya was one of my graduate school professors at Iowa State from whom I took analysis. Coincidentally, as soon as I said that, he recognized it because that was one of his professors back in the 1970s. And where was that?
In India, 73.
In India? Oh my goodness. So we didn't realize that we had this connection. We had even fewer degrees of separation between us. So without further ado, one of my colleagues from Wright State, Dr. Krishna Arasu.
Thank you. Thank you. It's nice to be back after almost 20 years, more than 20 years. Yeah, thanks for coming to the talk. I'll make it more informal at the very end. I use a computer to show some applications. So let me start with this my small object. So the way I usually lecture is most interactive. I ask a lot of questions. So slowly should be answering now. Have you seen this before?
Yes.
Good. It's a familiar object. Yeah, what is it? What is it?
Group consensus is matrix.
Oh yeah, I put this notation.
Determinant.
Determinant, exactly, yeah. So this is determinant of a 3 by 3 matrix, huh? Very good. I'm not doing yeah. I'll call this first row, second row, third row. Not a name, this is think of the vector. First place a vector. So yeah. Alright, if you do that, this is a number, yeah? This is some real number. So forget about the sign plus or minus. If you take its modulus, this has a geometric meaning. Does anyone know what it is? This number in absolute value has a geometric meaning. I'll give a hint. It's the volume of something. So this is the volume
Of the parallel of pipette,
very good.
in
Yeah.
which the three vectors you've defined define the sides of the parallel.
Very good. Exactly. Yeah. So if I picture, my pictures are not just in a row. So if you, in some sense, you draw the vectors in standing position. So you try to draw a box or parallel, whatever you call it. Yeah, its volume is exactly that. Yep. So there's something you learn in your elementary calculus. Okay, the question I'm going to ask, when is this the largest? When is this volume, of course, the largest? Look at the picture and tell me the answer. When is the largest? Oh, I am assuming, good question, I am assuming these are fixed, the lengths are fixed. Fixed length. Fixing the length of these, okay? There are a lot of vectors with the same length, so the what condition is the largest?
And they're orthogonal.
Very good. Exactly, yeah? This is the largest if and only if the three vectors A, B, and C are pairwise orthogonal. Good. And what is the maximum value? The max volume in that case is what? you know, from high school.
Sometimes with not height.
Exactly. So this is a rectangular box. Length times internal height. So it's the length of one side times the length of the second times the length of the third. Yeah? So that's an old story. In fact, I think it starts from here. As a mathematician, so there's nothing special about what we are doing here. Whatever is happening here is, I will call it here. What is that? You know what symbol is? Yeah, this is the so-called 3 dimensions, R3. The 3D space, okay? 3-dimensional real space, we call it. So that's what this is happening, yeah? That's where it's happening. Okay, well, mathematicians, for them, 3, just a number. What's your favorite number? 7. That's it? How big can you go?
2.
Oh, big. Big. Big number.
3,507.
I like that. 3,507. So look, very good, yeah. So look at that dimension, the real space. Play the same game. So what I will do is looking at the 3 vectors in R3, I'll be taking 3,507 vectors in this. Okay? So I'll do the same thing. So let us take the first vector, let us as a row, second vector as a row, and so on. The last vector, whatever as a row. So I will take a computer, this object. See the knowledge exactly the same. So this is also going to be a volume. Okay. So again, don't look for pictures, mathematicians. As long as it's abstract, they're very happy. So this is the volume of a box, I will call it. A box, okay? Box in a very sense. Whose sides are exactly what is there. Whose sides are, as we said, I'll just put in VR, where I equal 1, 2, up to whatever the number was. Okay? Same question, so I want to ask. So, when is the largest? A pair is orthogonal. And what is the largest volume of this box? The product of all the lengths. Okay? So that's exactly the same story. So that's where we start. Now I want to assume something instead of looking at in a random domain. I will write the coordinates. Assume that all the coordinates, I will call them write as Vij. Can I write as a Vij? Like a matrix where the ij entry is Vij. So assume that all these entries are in the range -1 to 1. It's called scaling. Everything is happening. It's a very compact space. Wherever the large one is, divided by magnitude. Assume everything has size for okay? So this is called a normalization. Normalization. So I ask the same question now. Okay, that's the same question. So let's actually let's go to Rn in general, go to any dimension. Alright, so the question here asked about 150 years ago actually. So look at Rn. There you look at n vectors, v1 up to vn, they're all in Rn. Where each coordinate or each component of the vector, right vector, they are in the unit. I could have written like this. In fact, the cutter is saying that I could have said it is in -1 to 1. They call it hybrid cube. Okay, send down hybrid cube. Alright. So now we already saw the answer. What is the answer? So if you look at the determinant of that large n by n matrix, alright. So this in absolute value, the largest value. What's the largest value? We just saw it. What's the largest value? Yeah, it is precisely the length of the first vector, and so on to the length of the last vector. Yeah. Alright. Well, and the equality rules. equality holds. What does equality hold? If and only if Vi dot Vj is 0. For all I not equal to j. That's the meaning of any two are perpendicular. Yeah? Any two vectors are orthogonal. Well, we know more in this case. Can you tell me what the largest value is? The largest volume, you can actually compute. Who knows the answer?
1.
No. You're very careful. It's not 1. It depends, it's a function of n. It's a very huge number. It depends on n. You got to do some work. Well, let's look at the largest value of this. How large can this be? Remember, all these are between -1 to 1. How do you compute the length of the vector?
Dot it with itself in square root.
Yeah, but distance formula, high school coordinate geometry. What is the answer? If you write the vector Vi as Vi1, Vi2, Vin, what is the magnitude? It's very right. This is the answer, exactly.
Yeah, you dot it with itself and square root it.
Exactly. So what is it? Square root. So square of this. So is sum of all the squares. Yeah. Is square each component is sum amount. I is j goes from 1 to n. Now look, how large is this? Look at it. All these are between -1, 1. So what's the largest value?
Each and 1.
The whole sum.
No, yeah, it's n. Square root of n.
Exactly. Square root of n. Okay. So square root of n is the bound for each factor. Now, how many factors do you have? N factors. Exactly. Okay. So here is the answer. It's exactly n to the n halves. So the largest value is n to the n halves. Okay. Square root of n multiplied by n times. Okay. Look right. Well, we actually know more. This is attained, and this is attained. When is it attained? We know more. The way we proved. When is this attained? Each value, what is the value of each Vij? Under what condition you get the largest value? What is Vij?
1.
Yeah, 1. Plus or minus 1. It could be 1 or minus 1. So if and only if I would say Vij is in modulus 1. It could be 1 or minus 1. Okay? So that's the time it happens. Is it clear? In fact, we have proved a big theorem. So this theorem is, as I said, 150 years old. So I'm going to put the theorem now. The theorem is exactly what we just proved. Theorem into Hadamard. I should know the year, I forget. So it's 150 years ago. Okay? You can look it up in French. Theorem is exactly what we said. So the maximum volume of determinant of an Vij in the end. Vij is from -1 to 1. So this maximum is no bigger than n to the n over 2, and equality is attained. If and only if two things happen. One thing is the values are actually equal to -1 or 1 for all I j. I'll give you something more. Geometry told you any two are perpendicular. Any two rows are perpendicular. Yep, that's what it proved. All right. Definition. Such a matrix. I don't like pronouns. Pronoun hater. You should know what such means. Somebody is explaining to me. Such a matrix is called Can you guess what it's called?
I'm gonna guess it's the title to your talk.
Very good. What is it? Well prepared, man. Yeah, it's called a Hadamard matrix. Hadamard? Why not, huh? Order n. It's called the order. The word order in the sense the size of the matrix n by n. Okay? So that's the definition. Again, there's a geometric meaning for all this, as I said. Notation. Well, notation. Notation. Bad notation. I'll tell you why. I'll call it H7. H for Hadamard, subscript N for precise. Okay? So that's the definition. Well, I could have kind of look at the abstract. You have all this. This is the motivation why this is used for application. That's why the term is not very difficult to prove. It's all proof already. All right. You can forget about all the geometry. You could just define like this. So here is the alternate definition. So all we do is take a matrix. I'll call it A sub ij. All right. It's an n by n matrix. Is said to be Hadamard. Is said to be Hadamard of order n, of course. Of order n. If only two conditions I'm going to put. First condition is the entries are where they should be. Takes only two values. Okay, all the entries, either ones or minus ones, as we saw. And the second condition, this is something you won't believe. All I will do is take a matrix, multiply by its transpose. Take this by the transpose. Okay? If you do this answer is very nice. In fact, you know the answer. You know the answer. If you can think of that form. So what is it? Can you guess? Let's take it, okay? Let's try this. So what is this very first entry? Needs some thinking, it's not hard.
They're all units. Shouldn't they all be ones?
One is, it's not quite one, it's much, a little bit bigger than one.
End of the 1/2.
Very good. It's not quite, you're right track, you're half right. You're half right. Yeah, see, you're taking this as a transpose, don't forget. Okay, let's think about how do you get a random entry? Let's get ij. If you want an ij entry, you take the ith row of this times jth column of this. Yeah? Jth column of this is the jth row of this.
And they're n.
Yeah, exactly, they're n. Okay? Well, almost always. They are n. Where are they n? Remember, it is n here. N is correct. Okay? All the way here it is n. That's correct. You know what's happening here?
So they are orthogonal.
Exactly. They're orthogonal. So what's happening? The vectors are orthogonal. Zeros. So it's such a nice answer. Multiply h times transpose. The answer is simply n times identity. That's it. Okay? So this is a very short definition. But if you get this definition, this is what I put in the abstract. Okay? But you lose the punch. There is more happening here. Okay? The geometry is so rich. It's not just a very simple algebraic definition. The geometrically this has a lot of information. You see that? Okay, that's why it is useful in applications. Okay, in today's world, everything is communication. So doing that, emailing, yep. Suffering, sorry. Don't enjoy it. Okay. So anything that you do, any communication here, it uses Hadamard matrix in some sense. Okay, if you want some privacy in your whatever you do. Okay, cell phones, no interference. So there are two issues. There is signal. There are both. There are two topics I would like to bring. One is called coding theory, Probably you've seen what it is. The other one is called cryptography. There are two areas in modern information theory or communication theory. So both are very important in today's world. Okay? They may look the same, but it's quite opposite. Okay? So this coding theory is mostly sending information over insecure channel, right? And then you want information to arrive with no errors, perfect communication. So cryptography, on the other hand, you know what that is, yeah? There is some security and all that. So this doesn't require security. So you need the both. They kind of related, at the same time one is against the other. Okay, it's very need balance. So in both disciplines you need this. Okay, that's the next part. Okay, so Hadamard matrix, yes, inside the main word that pointed out is the word orthogonal. Orthogonal. So orthogonal is very important in communication. Signals are going in all directions. Signals, okay. You don't want any interference. You want them to be orthogonal. That's really the main idea. So if all things go as vectors, you want orthogonality. Okay. So that's where it comes right. Very good. That's about motivation. Now you must have some obvious questions. Any obvious questions? Not really. After any time you see a definition from your professor in any math class, what's the first thing you ask? Pardon? Look for the test. Yeah, you need examples. I ask examples. In fact, any time some concept is going on, want some concrete examples. Okay? So let's go and provide some examples. All right? Obviously, example depends on this parameter. What's the parameter here? N. Very good. It depends on what N is. Okay? So let us play a very modest game. How modest you want to go? Smallest N you can think of. How small can you think of N? As small as possible.
0.
Yeah, but 0. Yeah, you're right. Yeah, that's not an empty set. I gotta stay with this. Yeah, you want to be a basic and actually look. Smallest N? 1! Thank you! Somebody knows how to count. N equal 1. Alright, I am looking for a 1 by 1 Hadamard matrix. Can somebody give me an answer? I'm looking for a 1 by 1 Hadamard matrix. Good! That's Hadamard, yeah? Look at the definition. Everything is satisfied, yeah? You have the geometric definition or this algebraic definition. Either one. Okay? You got 100 in the test. Good? Is it the only one? Is it the only one? Exactly. There's only one other choice, it works too. Okay, in this case, you have only 2 choices. Now, choices are very limited on the outlook. Okay? So, story about equal to 1 is done. Alright? Now, let's grow up. What comes after 1?
2.
2! Hi! Good class, good education. Very proud. Alright. Equal to 2. Okay? Yeah, here I'm going to give something away. I don't know how I can say it though. See, if you have a Hadamard matrix, you can do some transformation. You can multiply any row by its negative 1. Negate the row, it's still Hadamard. Any column, still Hadamard. Permute the rows, still Hadamard. Permute the column, still Hadamard. It's all the definition. I'm not doing it, okay? So the reason I said all this, because of all this, you can assume the first row is all 1, 1, 1, and the first column is all 1, 1, 1. With all the transformations. So it's called normalized Hadamard, I call it. So if we want a 2 by 2 matrix, I will assume the first row is all 1, first column is all 1. It is allowed. I just told you 1. Okay? I can assume that. Start. Okay? So which means I have to give you one more place I will see. But plus means plus 1 by the way. Okay? And I put plus is plus minus 1. What do I put? How many choices I have? I have 2 choices, which is the right one?
Negative is.
It has to be negative. You can't press again. You know, they're going to take it orthogonal. Okay? So the only choice is negative works. Okay? So in other words, there is only one normalized Hadamard of order 2. There are other examples. For example, you can multiply with minus, minus, plus, minus, that works. There are other examples. Okay? You can permute the rows, columns, multiply with an integral, but this is exactly, essentially the only answer. Okay? Good. All right, what comes after 2?
3.
Right. Good going. Pardon?
I like those questions I can answer.
I know. So I think just you take this like this, yeah, such easy, yeah. Oh, let's see, you can answer this question now. So yes, you know this is right, you know all this, yeah. Now play the game. So who wants to give the answer? Short and sweet answer. Short and sweet. Go fish. I like that. Doug said, nah, go fish. He's right. What does go fish mean? Oh yeah, exactly. Which means you go fish, it doesn't work. The answer is no. However you try, you fail miserably. What do I mean? What do you mean by that? Ah, now you talk. If you try filling it, you won't succeed. There is no Hadamard of 3. Who can give you quick reasons? Very easy to see why. See, I suppose plus or minus here, right? Whatever it is, the dot has to be 0. It can't happen, right? Why?
Will be symmetric.
Why?
All the products will be 1 or negative 1.
Very good.
Odd number of them.
Exactly. That's the theorem. Doug just proved the theorem. What's the theorem? Can you copy him and prove a theorem out of it? Theorem. Doug's theorem! Andrew's theorem. What is it? There you go. Theorem. He just proved. You know whatever he said? Did you listen to him? What did he prove?
First word.
For all this is work. Okay? Say proof first. Whenever it is not number, this fails. Unless n equal to 1. That's the only time. Okay? N equal to 1 it works. That's the only odd number. The moment you cross, it fails. Okay? So the theorem is, we write as a theorem, if there is a Hadamard of order n, then I'll make it simple. N equal to 1 or complete the sentence. You've understood what we just talked about in the past 2 minutes? That's theorem. Can you complete the sentence? If there's a Hadamard of an n, then either n is 1 or n is even. Very good. Simple logic. That's how you prove. What you prove, I'm writing affirmatively. I don't like negatives in connotation, okay? N is even. Exactly. That's exactly what you prove. Okay, we prove if n is odd, it doesn't exist. Okay? So that's exactly what it is. Is that clear? Very nice. So what's the next one?
4.
N equal to 4. Clean slate. So let's put n equal to 4. Clean slate. Pardon? Well, I want to, as it exists, there are many ways to do it. I'm going to give one here. This is my nicest, okay? I like it. My favorite. My favorite. You can check it works. So 4 by 4 is very symmetric. Put on the diagonal, minus, 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 minus. Everywhere is plus. You can see it works. All you have to see any kind of orthogonal that you can check how it works. 2 ones to negative 1. That's it. That's it. Okay? So this is a very pretty matrix, but this is Rich 62. I'm not going to do that. Okay? All right? Okay, what comes after 4? People are awake. Good. It comes 6 comes after 4. Yeah? If you said 5, they're sleeping. Okay? So, all right. N equal to 6. If you try, again, it needs some work. Answer is no. Yeah, this needs some work. one can show by doing some analysis. All you do is put a lot of plus here, and a lot of power plus here, and try to fit the first 2 rows you see your problem. I'm not, the proof is not hard. Now it's an exercise. Exercise is, this is always a student exercise. After your definition is given, after all this, you correct exercise for students. Where I should go? The theorem is just to state it. If there's a Hadamard or n, then either n equal to 1, or n equal to 2, or 4 divides n. So that's exactly the next exercise. Okay? It is little more work. It's not as easy as the proofs that Doug Andrews gave. Okay? But it's not too hard. Okay? It's just one more little analysis input. It's not too hard. Okay? So that's why he sticks it out. Okay? I'm not proving it. It's waste of time. Yeah.
Why doesn't your favorite matrix structure there extend to 6?
It won't. Yeah, if you try it, the inner part won't be 0. You need more negatives. The first and the second row already dot product will be 2 or minus 2. So you see there are 2 minus and 4 plus. So it's first. The first two are. It never extends. Yeah. So 6 doesn't work. Okay. So it can actually prove it has to be multiple of 4. Okay. Is that clear? So what comes next?
8.
Very good. Any good 8? Well, again, I won't waste your time. I will give you another term here. Or easy recipe. Like recipes, like it's a nice recipe. Recipe. Okay. I will give a definition first. Definition. Take a random matrix. I will call it Aij, which is any m by n matrix. Take another matrix B. I'll call it BKL, which will be a P by Q. The sizes don't matter. The sizes don't matter. So what I will do now, I'm going to define a new matrix. Given these two, define A times B. A times B is a huge matrix, very huge. Very huge. How huge? I'll let you figure out. So what I will do, I will take a typical entry from the left matrix, typical entry, and multiply by the second matrix completely for all I and j. At every position of this, I'm blowing it up. How do you blow that times this matrix? Okay, can you tell me how many rows and how many columns? That's easy. Give me the size. Number of rows and number of columns.
Is it m by n by p by q?
N times n by p by times q. Ugh, however you say that.
Well, I'll write it down.
N by q?
Yeah, it is MP by MQ. Yeah, there is MP rows. It's just a picture. It's a play a game, just picture. Yeah, it's a picture. Prove a picture. That's a very large thing. Okay. Okay. This don't even look at it. It's not worth looking at. Okay, just picture. There is what happened. Okay. The point is this has a name. So I think the popular name is called chronometer product. Chronometer product of A. Okay. For those who tend to know, you can say it tends to. So what it is. Okay? The reason I brought it down, can you guess why I brought it in? Guess the theorem, you're right. If you guess the theorem, you're right. With the context. I said it's a recipe, there's a context, what's the title of the talk?
The Hadamard matrix.
Hadamard matrix, yeah, that's it. With the new concept, you can guess what's happening.
It's probably the problem to Hadamard matrices is Hadamard.
That's it, huh? Very good, that's a theorem. Okay, there's a journal, whatever name is that you have. So you want to name? Publish on it? Okay. Yeah,
I'm not an algebraist.
Well, anyway, so you just want to see what's happening, the way we're developing. That's a natural theorem. It's a theorem. I'm writing that. I'll write in my language very, it's not very nice. If you take one of these, the answer is this. This is very bad language. You know what I'm trying to tell, right?
Yeah.
Hadamard over n, correct with Hadamard over m is Hadamard over nm. You know what's wrong with this language? It's not unique. The way I wrote it is, I tell you the story, but it's not very precise mathematically. There will be many of this type. Take any one of this type, take any one of this type, play this game, you get on this type. Okay? That's what I'm saying, alright? So, if I give you how many minutes you want, 1 minute, 2 minutes, can you get an answer for 8? How many of you are confident I can do it? You can get an 8. You're not confident? You don't know the copy.
I'm doing 4 and 2.
If you are a copycat, you should know it. Pardon?
I'm doing 4 and 2.
Exactly. He knows the answer, yeah. Here is a 4 by 4. There's a 2 by 2. Do it. It 8. Okay? Just play the recipe. You get 8, yeah? Remember, I used to ask that question. Suppose you want to grow up, right? 5 years from now, okay? How much money you want to have in your bank balance? Can you tell me? Okay, I'll give it to D. Okay? Deal is I will give you 1 penny. Just 1 penny. I'm serious. Sorry, okay? I'll give 1 penny for every Hadamard size you give me. If you give me a Hadamard new size, I'll give you 1 penny. A new size, Hadamard arts, okay? That's a D. 1 penny. That's all I can afford. No, you think I got this man. So you know sort of being bankrupt, right?
Yes.
I'm bankrupt. So in fact, with this little deal we have, you can anyways power. The whole world is yours. You see how? Who can prove a theorem here? It's a theorem. There's a theorem right here on the blackboard. It tells you how to make your jackpot. Yep. That's a theorem. That's how you prove it. Make you bankrupt. That's a theorem. This is one example. What else we look at 4? Look at this example. A simple example. You know how tiny it is? Take this example. Fade it in. This is very powerful. This is also a computer science department, right? This is a computer science department. So anybody in computer science here? You should be, yeah? Yeah? Computer science? Yeah, this is actually a recursive machine. This term is very, it looks very naive. Wow, but it is very powerful. It's a recursive machine. You keep on putting it back and back. That's a D. So now who knows the theorem? There is a theorem on the blackboard. Very rich. What is it? You have it? Theorem discoverers? No. For every positive integer, then we just Hadamard and put a subscript. I put a subscript. What's the size I can put?
No. 4.
N.
Maybe somebody say I didn't hear. No. It has to be an L. Given L, I can do that. I can fill in the blank and subscript. The proof is on the blackboard.
A multiple of L, so n to the n, n to the L.
L to the N.
I will give you L is like whatever 9 to 57. If you give me that, there is only one number I can put. The proof is in the blackboard.
LWE.
No, you have to look at the proof. Actually, you need a recipe. You need a recipe. Bill.
Julia.
Very good. He's my kind of a man. You want to work for me? I'll pay you. You want to come and work for me? I'll pay you, man. Actually, it's not a joke. I actually pay to do mathematics. I hire students to. Summertime, you want a summer job? Right. Okay. Very good. That's the theorem. What is my theorem? Exactly. Okay, it's a Hadamard offer 2 to the L. That's exactly true. This little example. The curve you use 2 times 2, 2 times 2 times 2. All powers of 2 are covered. That's all you know right now, okay? With the mechanics or with the recipe we got so far, with the very limited knowledge, for every power of 2, you know how to produce 1 of order dot product. The answer is right there, okay? You don't have anything else, okay? Even the next example, what's the next example which is not fitting it? The next example which doesn't fit the pattern is? Very good. You want to work for me too? I'm recruiting train now. N equal to 12, exactly, okay? That is not very exciting. If you want a 12, you got to split a little bit, okay? It is still possible. In fact, what I will do, since you seem to have a very good class here, I will put one of the theorem very quickly. If you want 12, there's a very small recipe again. Okay, 12 minus 1 is what? 11. Very good. So what I will do, here is my 12 by 12 matrix. Okay, I'll draw a picture and construct it for you. What is it? It is a 12 by 12 matrix. I already said you can odd with all plus and lazy to write, okay? So which means I have filled how many entries? How many entries I have filled already?
144. How many
I have
entries?
already filled? Counting. How many I have already filled? 23. So let's say 24, I could have said. I was going to say 24, let's not use 23, yeah? You have filled 23, how many more to go? How many more to go?
121.
121. How do you get 121?
11 squared.
Of course. I thought you say, I think you said 121, very good. 11 square, yeah? That's n minus 1 square is 11. So I'm going to fill these 121 entries very quickly, okay? In fact, I'll be very sneaky. I don't want to fill all of them. I'll only tell you what happens here. I will fill these 11 entries for you, okay? If you fill the 11, the rest will come by what you call cyclic shift. If you know this, next row I just shift to one position and ratchet around and so on. Okay? So that's the recipe. So I just going to tell you how these 11 elements are. To do that, this is what I will do. So there are 11 positions. So there are 12 columns, right? So I'll call the first column infinity. Don't ask me why. 11 left, I will call them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm labeling the remaining 11 columns as 0 through 10. Okay? Fair enough? Okay, now I'm going to fill, what are the entries allowed here? Plus or minus 1. I'm allowed to put out the 11 position. And how many plus and how many minus? How many plus and how many minus? I know that too. How many plus? 5. Okay. I can put 5 plus and 6 minus. That's the only way the first two rows we are talking. I have no choice. Okay? Exactly 5 plus, okay, and 6 minus. If you tell me where you put the pluses, do you know where you put the minus? Are you sure? Right, so I will tell you where you put the 5 plus. Okay? All I will do is, I will take this, I will take this, I will take this, I will take this. Haha, I had a thing. I'll take this. You know what I did? Okay, the way I do, who was following it? I was playing a little trick here. I said this first, then I went to this, then I went to this, then I went to this, then I went to this. You know what I did? What's the recipe? The way I did 1, 4, 9. After 9, I went to what are the numbers? Yeah, what did I do?
Integer squared mod.
Very good. That's correct. Yeah. It is really 1 square, 2 square, 3 square, 4 square, 5 square. Exactly. So these positions you put a plus. Haha. Plus. Rest are minus. That's it works. Okay. That works. Again, there is nothing special about what I did. The number was 11. You can replace 11 by any prime. 11 is any prime. Okay, what kind of a prime can you guess? I need a stipulation on the prime. Who knows the stipulation? I don't know random prime here. It's one stipulation.
Odd prime.
So,
Well, it's good. That's a good start. You're right. Odd. I can put any odd. For example, can it be equal to 5? If it be equal to 5, what am I looking for? 6 by 6, I said it doesn't exist. So that gives a clue. So what are the primes I'm looking for?
For n minus 1.
Exactly, for minus 1. Any prime of the form 4 minus 1 will work. Okay? Well, for mathematicians, they call it prime of 3 modulo 4. Any prime of 3 mod 4, if you take, the recipe works. Okay? Play the same game. Alright? So that takes care of 12. What comes after 12? Very good. 16. Can you handle 16? Sure. We have the theorem on the board, yeah? By the way, I should give a name for the theorem. The power of 2 theorem. The one I told you, even though he wants the credit, it is called Sylvester's theorem. The same Sylvester you see everywhere in algebra. That's called Sylvester Hadamard matrix. By the way, that matrix that I took, the 2 to 2, that is very heavily used in circuits, in electric circuits. So this is the electric is try one Sylvester Hadamard. Okay? So that's a very important thing. So 16, what comes after 16? 20. Can you handle 20?
Sure.
How?
With the theorem?
Because 19 is a prime. Very good. What comes after 20? 24. It works again. 23 is a prime. You can do it. After 24?
28.
28. Okay, then I'm trying to think. 28. So 28 is almost works. What is the problem with 28 minus 1? 27. Is 27 bad?
Yeah.
Why?
9 times 3.
It's not as bad as you think. 27 is not that bad. Why not? What's the other way to look at 27? How do you visualize 27?
3 cubed.
Very good. Who said that? Yeah, exactly. It is 3 cubed. Okay? So if you know some finite fields, or probably not finite fields here, there is a field with 27 elements. You can play the same game. The theorem I told you here is nothing about prime. Any prime power you can do. For a prime power, the same proof actually. It works in the field, Galois field. Exactly the same proof. Exactly squash in the field and so on. Exactly, okay? I'm not going to that. You get a little bit of field theory. Take abstract algebra will know. So that's why 28 works. After 28? 32. Problem with it? Oh, 32, power of Sylvester. After 32? Aha, 36? Yeah, 36 is that's the first time something really happens funny, okay? If you look at 36, because nothing works. Whatever you know from this point on, okay? Nothing fits. So in fact, the story for 36 is not very old, old for our standard. The theory is 150 years old. The 36 was studied probably about 60 years ago. It's 60, 70 years ago. Okay, so 36, a lot of things happened in the mid-60s. Okay, in fact, a Harvard PhD thesis was written on that. Okay, I'll give you an example of 36 very quickly. Very quickly. Let's see, very quickly, yes. 36. Well, the way I'm going to 36, I'm going to think of it as a 6 by 6 matrix. Nobody hate me for it. I'm not taking the Hadamard 66, okay? The 6 by 6 is what I call a placeholder. A placeholder. How many cells are here? 36 cells, okay? So it's really, I'm going to do the big 36 matrix. So the point is to construct that. So I'll start with 6 by 6 and kind of put it here. The way it is done, I'll get you the same what I did. 1, 2, 3, 4, 5, 6. 5, 6. 6. Let's start this. So what I have done, I have put how many minus here? How many minus?
16.
Wait, I have to do 16. Is it?
It is 16.
I think. You must be right. Yeah.
6, 5, 5.
Okay. No, I am worried. I am worried. I am worried.
I don't think it works.
It won't work. That's why I'm worried. So I'm supposed to only 15 of them. So my example is not right. So this all. So I need to press it. Now does it work now? Better. No, I can take it back. you're not supposed to do this because you don't want to make it. Yeah, I'm supposed to 15 plus. This is null slide. Okay? So take this, diagonal, take this. So that's 15 elements. Okay? So this here, think of it as a you should know little group T. Think of this as Z6 cross Z6. You know some group T here. Okay? So this is going to be an object like the one I did, the cyclic shifting. The first row is exactly the copy of this in the group. And the rest of it is what's called a Z6 cross Z6 action. For a cyclic group, it's one shift, there's a group T. So that gets it. So it's a very rich tree here too. I'm not going to talk, okay? So that's the way the heart of this was developed. So in fact, we have a big result of this. It's something due to me. I'm proud of that. So actually we proved this is not nothing special. Actually, you can do Z2 times any power of 3 cross Z2 times any power of 3. You can play the same game, but it's very deep group theory. You can get marks. Okay. In fact, after I did this, I started getting a lot of grants from the engineering people. Love it. They started giving lots of money. This brought real money I got. Okay. So this is really very important. So that's well. If you keep going, well, when do you stop? You may ask. You must be tired. So where does the story end? Can I ask a question? A fundamental question. There's a question here which should bother you. Should you be bothered? There's an obvious question. Burning question. What is the question?
Multiple 4?
Yeah. This is, if I give you a random multiple of 4, can you give me a Hadamard of array? Yeah. Good question. Given any n, which is a multiple of 4, 0 mod 4, does there exist a set of negative? That's the question. Okay. Can you guess what the answer is?
Yeah.
No one knows. Yeah, the answer is that people believe it is true. It's called a Hadamard conjecture. Okay? Which is still not solved. Even though asymptotic results exist, you can do asymptotic, they always exist. Okay, given another, I can state a nice theorem. You will believe, but it has to be true. So things happen to smaller for difficult. Smaller are the troublemakers. Okay? But I can give, I should know, is 67 a prime? It is. Okay. What is 4 times 67? 268, I believe. It is 268. Oh, you have a computer. You can Google now? Are you on Google? Any search engine?
402.
Can you search?
For 6 times 7?
No, I'm not. I'm asking, can you search if I tell you a Google search?
Yeah.
Oh, good. Put Hadamard space 268. The first entry is a paper. You have to because Hadamard space 28. Read the title of the paper.
Show all busmen? I might not have followed it right.
I'm sorry. What is it?
Hadamard, H-A-D-D.
Sorry. Yeah. Yeah, the reason I brought it out, it's almost time, so I only get to the application. So there we go. You got it, right?
Yes.
The reason I brought it in, how old is the paper? 2000? 15? No.
1985. First one that came up.
Was Springer Verlag?
Yeah.
Springer Verlag.
No.
The existence of Hadamard matrices where 268 is established more generally.
Suppose there exists units in the matrix order.
No, 268 was done when? No, 85. No, not that. It happened much later. It happened in the 2000s.
Yeah, it was by, 1985.
What is the other name of the authors?
S-A-W-A-D, squatted.
Okay, so
K squatted. S-A-W-A-D-E. You're quite.
1985?
Here, you look at it.
No. Yes. Oh, you're right.
I spelled it right this time.
The internet never lies.
Really? Is that old? I was really old. I don't remember. You know what? the story is, it doesn't give the answer, it tells you the algorithm how to get it.
Oh.
Okay, okay. The actual construction was done by two Iranians. One was a student like you, and the other one was an old prof like me. It's really a team, a student and the computer. There's an algorithm. It tells you how to reduce the search.
Yeah.
Okay, using 4 blocks of something size, and the search is completely wrong. It happened just less than 20 years ago. I know about the authors, that's why it didn't happen. The emails are floating around, so it's 268 years. And the next ones are very, it's 400 next time, what I forget the next one, okay? That is still open. It's 500 something. I will get that, okay? So the point is, 4 times prime is hard. The bottom is 4 times prime is hard. 4 p a prime. In fact, there is a little theorem. If you can solve the problem for 4 times a prime, you would have solved this. That's a little, that's a theorem. Okay, so proving this 4 times prime is hard. Okay, so that's the thing. Then we come to a very difficult problem. There are a lot of research you can look online. All right. Anyway, so I was going to put some, since I'm already up to the time, I didn't know it. Almost off.
Officially, we ended 5.
It is 5. It is more than 5. So it means I'm over. Okay. Anyway, so I have some slides for those. Well, I can send you some papers and applications. You may think this is all why it looks nice mathematics. Mathematics will love it. Okay. So, but it turns out this has real applications in many areas. I already told you some. And people in electrical engineering, they love this. Okay. The Sylvester Tyler, other applications from that. And people in the cryptography, according to statisticians use it. You're a statistician.
Yeah.
Yeah, people in design, there's something called optimality in statistics. I remember anything with optimal, there are many kind of optimal, that optimal, this optimal. The one you saw was D-optimal, determinant optimal. Determinant optimal. In fact, the Hadamard is sitting everywhere. Of the proofs of optimality, they'll say Hadamard, they'll be that optimal. So this really is optimal in many senses. So it's a lot of, we're talking about a very rich area. Okay? And anything which is not many unsolved problems still. Okay? The problems are still open. And I talk about orthogonal only, pure orthogonal. There is a big research where the orthogonal is kind of what called nearly orthogonal. Instead of having 0 orthogonal, it's a concept you can't expect. You got a number of 4. People accept inner product to be -1 always. That's allowed. That's not good enough for as good as 0. Okay? There's a rich theory for that too. Okay? In fact, one of my papers just appeared last June in ITP Transaction Information Theories in Electrical Engineering Journal. It's a very long paper. The typed version is about 100 pages long. It's condensed. It's very long. Okay? The mathematics is still not explored completely. I'm hoping some experts will come and understand and solve the problems we can solve. The proof I have, I don't like the proof. Okay? The proof is very ugly, it's right, but the proof is, I don't like it. It's very too combinatorial, a lot of graph theory too. But we'd like to see a better proof, key proof. Okay? Just like that. There's so much to be done. So if you want, I can send you some papers. Come to Wright State, I'm not too far from here. Incidentally, we have a new PhD program. I was going to the slide. I'm the director of it. We just finished the first year. We just admitted the second year next year. We prepared it too. It's called Interdisciplinary Applied Sciences and Mathematics. You see, interdisciplinary nature, and we already put, my students already started working in industry. First year they finished. They're in industry already, they are being part. So you get a job right away too. They have connection with industry, the Air Force, okay? So if you're looking for a PhD career, okay? Still, you do what you like to do, still you make money. It's one option, okay? Right, okay? So that's it, thank you.
I'm sure Dr. Arasu will be willing to stick around for a couple minutes in case anybody has any further questions, or especially questions about their new PhD program. Thanks again, see you all in 2 more weeks.